Welcome to Programming Fluency. This is section 3.3, Loops. So far your programs run each line once from top to bottom. In this video, you learn how to make a program repeat a block of code. C gives you three kinds of loop: for, while, and do while. Let's begin. Now we turn to loops. A loop repeats a block of code, checking a condition each time to decide whether to keep going or stop. Let's see the three kinds C gives you, and when to reach for each one. This is the plan for this video. First, we look at why we need loops at all. A loop lets you repeat a block of code instead of copying it over and over. Next, you meet the while loop. It checks the condition first, and then repeats the body as long as that condition stays true. Then we look at the for loop. It packs the setup, the condition, and the update into one line, which makes counting compact and easy to read. After that, you learn the do while loop. It runs the body once first, and only then checks the condition. Finally, we cover how to choose the right loop, and how to avoid two classic mistakes: the infinite loop and the off by one error. Why do we need loops? Suppose you need to print the numbers 1 through 10. With what you know so far, you would write 10 separate print statements. Now suppose you need 1 through 1000, or the count is not fixed and you keep going until some condition is met. 10 print statements will not scale. You need a way to tell the computer, repeat this block of code. That is exactly what a loop does. It runs a block again and again, checking a condition each time. The while loop is the simplest one. It checks a condition before each pass through the loop. If the condition is true, the body runs. If it is false, the loop ends. This definition sums it up. A while loop evaluates a condition before each iteration. In C, true means non-zero and false means 0. Because the check comes first, the body may run 0 or more times. This is a while loop that counts to 5. The variable count starts at 1. The condition is count less than or equal to 5. While that stays true, the body prints count, then does count plus plus, which adds 1 to count. After the fifth print, count becomes 6, and 6 less than or equal to 5 is false, so the loop ends. Notice the three moving parts. First, you initialize count before the loop starts. Second, you check the condition each time before the body runs. Third, you update count inside the body. If you forget this update, the loop runs forever. Let's trace the loop step by step. Each pass checks the condition, then runs the body. On iteration 1, count is 1. 1 less than or equal to 5 is true, so we print 1, and count becomes 2. On iteration 2, count is 2. Still true, so we print 2, and count becomes 3. On iteration 3, count is 3. We print 3, and count becomes 4. On iteration 4, count is 4. We print 4, and count becomes 5. On iteration 5, count is 5. 5 less than or equal to 5 is true, so we print 5 and count becomes 6. Now count is 6. 6 less than or equal to 5 is false, so the loop ends. The body ran 5 times, then the condition failed on the 6th check. This figure shows the shape of a while loop. Let's walk the 4 points on the right. Initialize count to 1. This happens once before the loop. The condition, count less than or equal to 5, is tested at the top of the loop. When the condition is true, the body runs and count is updated. Then the arrow loops back to the condition. That back arrow is what makes it a loop. When the condition is false, the false arrow leads out of the loop. That false arrow is what stops it. The for loop packs the setup, the condition, and the update into a single line. It is the most common loop in C, especially for counting. A for loop has three parts in its header, separated by semicolons: the initialization, the condition, and the update. The initialization runs once. The condition is checked before each pass. The update runs after each pass, just before the next check. This is the same counting example, written as a for loop. Read the header left to right. I equals 1 is the initialization. I less than or equal to 5 is the condition. I plus plus is the update. The body just prints I. The output is identical to the while version. It prints 1 through 5. The difference is structural. In the for loop, the initialization, the condition, and the update all sit together in the header instead of being scattered around the code. This figure shows the execution order of a for loop. Let's walk the three parts. Step 1 is the initialization, I equals 1. It happens exactly once before the loop starts. Step 2 is the condition, I less than or equal to 5. It is checked before each pass. If it is true, the body runs. Step 3 is the update, I plus plus. It runs after the body, then control loops back to the condition. One more thing, the variable I is declared inside the header, so it exists only inside the loop. Every for loop can be rewritten as a while loop and every while as a for. They are equal in power. The difference is readability. Both loops on this slide print 0 through 9. Use a for loop when you know the count. Counting, ranges, or stepping by a fixed amount. The for loop keeps all three pieces in one place, so the structure is easy to see. Use a while loop when the count depends on a condition, waiting for a value to reach a threshold, or reading until a special end value appears. In those cases, counting is not the point. The three-part header makes common counting patterns easy. Let's look at 4 of them. Counting up from 0. Start at 0, condition I less than n, update I plus plus. This runs exactly n times, giving I equals 0, 1, up to n minus 1. This is the C convention. Counting up from 1. Start at 1, condition I less than or equal to n. Use this when the counter is a human count, like month 1 through 12. Counting down. Start at n, condition I greater than 0, update I minus minus, which subtracts 1 each time. Stepping by 10. The update is I plus equals 10, which adds 10 each pass, giving 0, 10, 20, and so on. One of the most useful loop patterns is accumulation. That means building up a result across the iterations. This program computes the sum of the integers from 1 to 100. The variable sum is the accumulator. It starts at 0. Each pass, the line sum plus equals I adds the current value of I to the running total. After the loop, sum holds 5050. 2 rules to remember. Start the accumulator at 0 for a sum or at 1 for a product, and update it inside the loop. The while and for loops check the condition before the body, so the body might run 0 times. The do while loop is different. It checks after the body, which guarantees the body runs at least once. A do while loop runs the body first, then checks the condition. If it is true, the body runs again. If it is false, the loop ends. The body always runs at least once. Watch the semicolon after the closing parenthesis. The do while is the only loop that needs one. Forgetting it is a common error. A do while usually gives the same output as a while. The difference shows up when the condition is initially false. Here count is 10. The while condition, 10 less than or equal to 5, is false right away, so the while body never runs. Then we reset count to 10, and the do while runs its body once, prints, and only then checks the condition. So the while body is skipped entirely. And the do while body runs once before the check. The only output is the do while line. This figure contrasts the two loops side by side. In the while loop, the decision comes first. The condition is at the top, so the body might be bypassed and run 0 times. In the do while loop, the body comes first, and the condition is below it. So the body always runs at least once before the first check. A good use is input validation, where you must ask the user once before you can check the answer. This table helps you choose the right loop for the job. Let's read it row by row. Known number of iterations. Use a for loop. The counter lives in the header. Condition checked before each pass, where it may run 0 times. Use a while loop. The body must run at least once. Use a do while loop, because the check happens after the body. Counting through a range. Use a for loop, since the init, condition, and update sit in one line. Waiting for a condition to change. Use a while loop. No counter is needed. In practice, for is the most common. Use do while rarely, mostly for input validation and menus. If a loop's condition never becomes false, the loop runs forever. This is called an infinite loop. The clearest example uses the constant one as the condition, while open paren 1 close paren. Since 1 is always true, the condition never fails. Programmers sometimes do this on purpose, together with break, to exit at a chosen moment. But accidental infinite loops are bugs. The classic one is forgetting the update, so count never changes and the loop prints forever. The fix is to add count ++ inside the body. If a program hangs and stops responding, press Ctrl+C in the terminal to stop it. This is one of the most common programming mistakes, the off by 1 error. The intent is to print 1 through 10, but the condition is I less than 10. That prints 1 through 9 and misses 10. When I reaches 10, I less than 10 is false, so the loop ends before printing. The fix is to use less than or equal to, so the endpoint 10 is included. Remember two safe recipes. To count from 1 to n, use I equals 1. I less than or equal to n to run exactly n times. Use I equals 0. I less than n do not mix them. Let's recap. Loops let programs repeat code. C gives you 3, each suited to a different job. The while loop checks its condition before each pass, so the body may run 0 times. Use it when the number of passes depends on a condition. The for loop packs the init, condition, and update into one header. It is ideal for counting. The do while loop checks after each pass, so the body always runs at least once. Accumulation builds a result across passes. Start the accumulator at 0 for a sum and at 1 for a product. And a loop whose condition never fails is an infinite loop. Press Ctrl+C to stop it. Next, in section 3.4, Loop Control and Nesting, you will learn break and continue to control a loop precisely, and how to nest loops inside each other for multi-dimensional patterns.